Hello, everyone. So for today's webinar, we're going to talk about first some introduction about Maplesoft offering tools and services, and then I'm glad that David can join us. He will be talking about the JMAG and JMAG RT technology. And then Jonathan will go into MapleSim and basically show the JMAG components in MapleSim models. And then we will have hopefully time for Q&A. So I'm going to take a few minutes and set the scene for this webinar, and also discuss and introduce our engineering solutions, and also the role of symbolic technology in the way we can help accelerate the model-based design. So what we do in Maplesoft, we have two softwares that are used for research and engineering applications, Maple and MapleSim, which we will have a quick look later on in this webinar. And another layer to that is our advanced tools, our expertise that we offer to help engineering problems. And these solutions would involve product design validation through modeling and simulation of the system, physics-based system-level simulations, and these models and simulations can be used for a number of in-the-loop applications, such as hardware in the loop, with the optimized code that we can generate from the system-level models that are created in MapleSim. And using those models, we can provide analysis tools and design tools that go through the model, and based on the requirement and the specifications of the users, they can easily and quickly look at what-if scenarios. Other areas of expertise that we can offer are the model order reduction and symbolic simplification for use in model predictive control, which is something that our advanced research group will be taking on. So the big picture in terms of the interconnectivity of our tools and the engineering solution is, as you see on the picture, we have MapleSim, which is the environment for physical model creation, physics-based simulation models. This environment is tightly connected to the Maple, which is the basis symbolic technology behind all of our engineering and computation tools. And here we can create what I refer to as design tool or analysis tools, such as parametric analysis and optimization. So these environments will together be where you create your model and then perform advanced analysis or move towards a design tool. What makes this cycle complete is being able to deploy that code to other environments, for example, for real-time applications. So what we can do is, based on the models that are created and analyzed and basically fine-tuned, you can create C code, and we maintain that the C code that we generate from our models that are created in MapleSim are the fastest for the runtime and will enable the users to achieve real-time performance. In all, this cycle will help reduce the development risk and assist in producing better products, and in all that in a shorter time. So just a case study from one of our customers, a major automotive OEM, just a very brief description. The project involved incorporating higher fidelity electric drives into a vehicle model, and the purpose of that model was for assessing its performance and also doing control design. The reason for adding the higher fidelity with more detail into the model on the electric motor side was to look into the torque vibration, which are caused by the variation in the motor magnetic field. So that was important, and that was accomplished by introducing the components from JMAG, which we'll be discussing later in this webinar. And the expertise provided towards a complete solution was, first of all, modeling the electromechanical system in MapleSim, towards creating a complete electric vehicle model, and also was in the software development, which led to creation of a connector for JMAG technology. And the outcome of this project was a tighter integration between a 3D analysis, which is the vehicle chassis interacting with the environment and going through maneuvers, and 1D simulation, which involves the powertrain and electromechanical system. Having all of those in one location with access to higher fidelity, more detailed FE-based models provided a faster design workflow and development process. Just bringing the design V, and to give a kind of put into perspective where our simulation software, MapleSim, comes in. As the requirements are defined, when we get to, in the system design phase, when we get to virtual prototyping and control design, MapleSim technology is invaluable in creating fast and accurate models towards achieving the rest of the design process. A very brief note about the technology, what we call physical modeling and acausal modeling. So in traditional physical modeling approach, we have a concept, and that concept is then broken down based on physics into set of equations, and depending on the approach for computer simulation, more work needs to be done to program that into towards a numerical integration for simulation. So this approach is, of course, time-consuming and prone to a lot of mistakes. And the new approach is what is implemented also in MapleSim, and this is working from concept to the model. Basically, creating models this way eliminates the model derivation part and make that automatic by the computer. So MapleSim, as you can see on the model on the right-hand side, for this simple double spring damper mechanism, and a causal model in an environment such as MapleSim will basically have a one-to-one correspondence to the model that we started with. And that will make it a lot easier, faster, and more accurate in terms of bringing a concept to a dynamic model that can be simulated towards a variety of analysis, such as those that I mentioned in the previous slides. The model derivation part, as I mentioned, is done automatically, and through the technology that Maple powers for MapleSim, we have access to the equations that are automatically generated, and these access that we have to this equation provide us a very direct tie to the underlying physics of the system that we are trying to model. Of course, having access to equation provides some other benefits, such as doing further advanced analysis on the system. You can think of parametric optimization, the sensitivity analysis, and all that. I mentioned that the models that you create in the MapleSim environment, you will be able to create code, C code, from them. And one of the usages that we provide for that code is through our Simulink connector. So MapleSim works very well with Simulink as the environment for creating plant models. And these high-fidelity models that are created in MapleSim are optimized for extremely fast simulations, which provides utility to perform real-time simulations. This is a few examples that benchmark that we have done, looking at some multi-body systems. The one on the top is a Stuart platform that has controller for motion control, and you can see the timings for a specific run between MapleSim and two other similar products. And the other one is the one in the middle is the Stuart platform without control. It's just force-driven, and the comparison shows the code that is generated from the derived equation, which is compiled and run, is much more optimized, which results in a couple of order of magnitude faster simulation. And the last one is the six-link pendulum, which we see similar gains in performance, which then translate to being able to do a lot more in terms of optimization or adding more detail to a real-time analysis. So what we're going to discuss today, with that kind of setting the scene for the environment on the MapleSim side, David will, hopefully he's online, and we'll be talking about the technology of JMAG and JMAG RT, which is a FEA-based electric motor simulation and analysis. And we can, in the connector that we have created for MapleSim, bring in the results of that analysis, the way that is provided to MapleSim to create a system-level model that incorporates the multi-domain approach that is provided in MapleSim and connect that to high-fidelity models of electromechanical systems. So with that, I will pass the presentation to David. After David's presentation, Jonathan will take over and take you through a few examples in MapleSim. Thank you.
Excellent. All right. Well, today I'm going to talk about linking a JMAG RT high-fidelity machine model block to MapleSim. So what I want to talk about today is an introduction to JMAG, and then talk a little bit about what defines high-fidelity system modeling. Then we'll talk about how to create a high-fidelity machine block and kind of summarize what we see going on in RT or in the high-fidelity machine environment. So first of all, who we are. Well, JMAG is a software package that's manufactured by the JSOL Corporation. JSOL itself was established in 2006, but it was based on a split from the JRI, or Japanese Research Institute, which was established in 1969. JMAG was actually created in 1983, so we're a little over 30 years old now with our software data, so a lot of experience. The JSOL Corporation is a very large company with 1,300 employees that has offices in Tokyo, Osaka, Nagano, and Sapporo, with the main business units being IT consulting, system integration, and CAE, of which JMAG is one of those CAE packages that they have developed. JMAG distribution occurs through a network of distributors located globally. The distributor in both North America and Europe is PowerSys Solutions. So JMAG is a finite element analysis software for electromechanical design. This is just a kind of a simple 3D rendition we have of an interior permanent magnet machine. We use the machine a lot in our literature because it's probably the most common electromechanical device, but we do work with a lot of different electromagnetic devices or electromechanical devices such as linear machines, stepper motors, actuators, etc. This is a slide that I usually like to show. It kind of gives an overview of the thrust of JMAG, which is to emulate a virtual test bench. So any measurement that you would take on a test bench, we want to be able to replicate in software. But we also want to go beyond just that measurement data and provide more insight on what's actually occurring inside the machine. So things like torque versus speed or losses or sound pressure are things that we can measure, but we also want to look at distributions. We want to look at the joule loss distribution, the flux density distribution, the efficiency map capabilities, and even force distribution inside the machine. So again, anything that you would take a measurement of, but also more insight into where those measurements are coming from. The JMAG product line starts with JMAG Express. This is our kind of our entry-level tool. It's a template-based design tool that allows you to very quickly and easily set up a rotating electric machine based on some common templates for rotating machines. So things like brushless motor, IPM, SPM, or brushless, interior permanent magnet machine, surface permanent magnet machine, brushed motors, switch reluctance, universal motors, etc. can be set up very quickly in JMAG Express. Next, we move to JMAG Designer. This is kind of the heart of our analysis package or analysis tool chain. This is where all the models can be run in much greater detail. So we can take our very basic JMAG Express model, move it into JMAG Designer, and run a much more thorough analysis in JMAG Designer. JMAG Designer can also link to other packages through our JMAG RT motor model block, so that's what we're going to get into today. And that's how we can link to well, first of all, we can go to JMAG RT Viewer to visualize some of the machine performance parameters. But we can also link to hardware-in-the-loop simulation programs, and I wanted to bring that back, and software-in-the-loop simulation programs such as MapleSim. JMAG Designer can also link to programs like CATIA or Abacus to do structural, thermal, computational fluid dynamics, basically multi-domain simulations. But again, the thrust of today's presentation is how we can use that JMAG RT motor model block to link into software-in-the-loop simulations through MapleSim. So high-fidelity system modeling. Well, to begin with, motor complexity is increasing. So there's increased demands on efficiency, higher speeds, and smaller size. What this entails is that motor designers must use interior permanent magnet machines with rare earth magnets that have high torque and utilize reluctance torque and require flux control. So to increase the power density, they're also employing things like concentrated windings to reduce copper losses and compression at the coil ends, again, to reduce the overall size and improve the thermal efficiency. But this type of machine has strong nonlinear and non-sinusoidal properties. So our basic surface permanent magnet machine is very nicely behaved. If we look at the back EMF voltage when we spin that motor, it's very sinusoidal or closely approximating sinusoid. If we look at these more advanced motors, what we see is that the induced voltage has a lot of harmonic content. So what we get is that, let me go back. What we basically have is that the motors themselves are increasing their level of complexity. So we don't just need a high-fidelity solution for a simple motor. We need a high-fidelity solution for a very complex motor. And what do I mean by a high-fidelity motor model? Well, what's demanded is that we have to account for magnetic saturation. We have to take into consideration geometry factors such as tooth shape and magnet location. And we have to include property effects such as temperature, basically the demagnetization of the magnets due to temperature, the increase of the resistance due to temperature, etc., have to be considered in these types of models. So JMAG RT becomes the mechanism for providing a high-fidelity model, which can then encompass all of these traits into a software-in-the-loop, hardware-in-the-loop, or model-in-the-loop simulation environment. So what's the benefit of high-fidelity system-level modeling? Well, as I said, the demands on the motor and the controller are increasing. And so being able to take your motor and simulate a high-fidelity motor and couple it to a simulation of a high-fidelity power supply and then an advanced controller, by being able to couple those three subdomains together, we get a much better system-level simulation. What this gives us is that we're then able to achieve a higher system efficiency using lighter and smaller component sizing and have a quiet and more comfortable ride using lower noise and vibration. We can also reduce development and completion time, again, by being able to virtually prototype our machine instead of going through and actually having to physically prototype all of these subsystems, put them all together, and then test them, and then go back to them and say, okay, that was the first round, let's make some improvements in this domain and then try it again. And in the end, we come up with a safer and more reliable product. So system modeling. Accurately simulating control and operating conditions is critical to achieving peak system performance. Traditionally, the machine design, control, and testing teams have been separated. The machine design team provides rated performance parameters to a control team that then uses a simplified machine model to design a controller to operate in a simplified test environment. This makes it difficult to develop a system-level simulation that is accurate across the entire operating range. JMAG RT is a tool that allows a machine designer to develop a high-fidelity machine model and then share this model with a control designer. The RT model block is based on a finite element analysis simulation, so again, it's a very high-fidelity model. MapleSim is then a tool that can facilitate the creation of a high-fidelity system-level simulation by utilizing the JMAG RT model block. So the requirements for model-based development. Real machines have nonlinear and non-sinusoidal properties and cannot be described by simplified models. So if we have our simple machine system model, we have our controller, we have our inverter, and we have our motor. Well, the inverter is going to have dead time and device properties that need to be considered, and the motor is going to have saturation properties, cocking torque, ripple torque, and other nonlinear properties. A plant model or motor model, or the plant model or motor model's precision is particularly an issue in model-based development. Motor model precision is the key to the success of model-based development of a machine drive. So we have to have our motor model approximately equal to our actual machine. Anything less than that, or anything that doesn't equal our actual machine, is not going to be give us a high-fidelity system-level simulation. So what is JMAG RT then, or how does that fit into the picture? Well, a well-constructed FEA machine model can provide accurate performance predictions at the trial points across the machine's operating range. The problem is that this would take too much time to actually do a single FEA run at each operating point and then translate that data into a design sheet for the controller development team. To overcome this, you can do a direct coupling between JMAG FEA and a control model in a separate program or a separate control model. This will reduce the analysis time, but it's still prohibitively long in most cases. So the solution becomes using a JMAG RT model block that captures the performance parameters based on FEA analysis and turns them into a lookup table that can be used as a block in numerous simulation environments. So we have our FEA model data, so again, our very high-fidelity results coming from FEA, motor properties calculated, accurate torque, accurate inductance mapping, accurate flux linkage, and iron losses. And we convert all those numerical results into a block, shown here, that can be taken into a system-level simulation. So now we can take our motor drive, interface it with our high-fidelity motor block, and then come up with a vehicle, or in this case, a vehicle dynamic simulation that's going to give us a very accurate response for how that motor would perform in that simulation environment. High-fidelity motor modeling basically comes down to being able to capture the nonlinear performance. So if we look at things like the inductance properties, we can see that at 0 amps, our IPM motor's inductance varies according to a mechanical angle because it has saliency. This is almost a textbook example of the variation of the inductance as a function of the position, or as a function of rotor position. As we increase our current, we can see that now our nicely well-behaved, very easy to describe model, it's not easy to describe. When current is added, the inductance properties are greatly affected and the curved surface becomes very distorted. When we get into really heavy saturation, what we find is that the distortion of that map is even worse. So the inductance properties are really distorted due to the magnetic saturation. So trying to come up with a numerical representation of this inductance map would be nearly impossible. The same thing goes for torque. So at 0 amps, variations are just due to the cogging torque, and usually the cogging torque is very small. As we increase the current, what we find is that the torque generated, or more torque generated, brings in more variations. And again, at higher saturation, that goes even further to say that that applied torque, or that output torque, varies pretty significantly. And so what we have is that in order to capture these properties, the inductance and then the torque properties, and as well as the flux linkage, we can't come up with a numerical equation. We're left with coming up with a block, or that RT model block, that takes the data, or takes that numerical data and puts it into a lookup table form that can then be used in our high-fidelity system simulation. So what do I mean by this? Well, let's take an example of evaluating a drive system. Detailed drive system evaluation using JMAG RT and model-in-the-loop simulation. And let's see, we're going to confirm the current and voltage waveform, and we can obtain iron loss in motors driven by PWM inverters. So in this example, we're taking a look at a stepper motor where we're going to have our controller and our stepper drive, and then our input to that stepper motor, and then our high-fidelity stepper motor model in that environment. So this is, again, a lookup table of the results. And if we look at the results in this case of the transient analysis command versus actual position of the switch reluctance machine, we can see that our command position, or our desired shaft angle, is shown in red. The actual shaft angle is shown in green. And so, again, we're seeing that the command, it isn't a nice progression up into that command variable. So there's actual machine dynamics that are at play that mean that the response isn't going to be a nicely predicted linear response. Other JMAG RT usage examples, we've seen that JMAG RT, from our perspective, we've seen JMAG RT used in the development of advanced machines drive systems. It can also be used for system-level simulations, and the following couple slides demonstrate how RT modeling can be used today. So this is an example taken from our users conference given by Mitsubishi, where the conventional motor model that they used did not capture the machine's performance. So their actual measured performance, you can see, shows a lot of nonlinear behavior, but the simulated motor performance is all very nicely behaved. So we're missing all that dynamic content that is actually occurring in the machine when we use a very simple machine model. However, if we go to a JMAG RT model block, now we can see that all that dynamic simulation, or all that dynamic response, much more of that is included with the JMAG RT motor block than the conventional motor model. So again, what we see is by using a high-fidelity machine block with a lookup table representing those complex inductances, those complex torque responses, now we can capture a lot more of the dynamic behavior that's actually inherent in the machine. So to generate a JMAG RT model block, it's pretty simple. There's 4 basic ways to obtain that JMAG RT motor model. We can get it from JMAG Express, JMAG Designer. We can actually take measurement data and convert that into an RT block, or we can use our JMAG RT motor model library, which is available on the JMAG International website. To generate that simple JMAG RT model from Express, all we have to do in JMAG Express is create our model using our template-based tool, and then click the RTT button. And once we click that RTT button, now we're going to get our RT motor block that then we can bring into our system-level simulation environment. To generate an RTT file from JMAG Designer, or RT motor block from Designer, first we create the FEA model in JMAG Designer. And this can come from JMAG Express, or it can come from any other ways to bring in the geometry. So we can use our links to SolidWorks, Pro Engineer, CATIA. We can bring in the geometry that way. We can create it internally in JMAG's 2D and 3D geometry editor. But the end of the story is that we create a model. We create a model, and then we choose our RT fidelity. We set our analysis conditions, and we generate the RT file. When I say RT fidelity, I mean that we have 2 levels of complexity. We have a basic LD-LQ model, which it only captures magnetic flux. So this is good for basic system-level design. So again, we're relying on basic DQ type relationships for our machine. The next level of complexity is the spatial harmonic model, which captures magnetic flux and current flux, and this is good for much more advanced controller designs. So in order to run the spatial harmonic model, you must also run the LD-LQ model. But at the same time, the spatial harmonic model, it differs from the LD-LQ model in that it's done in the ABC reference frame. So JMAG RT motor models can be distributed and used without disclosing information such as geometry of the motor and the materials that are used. So this is, again, a way that we keep important data like geometry confidential. So those RT motor blocks, you can shift those around or send those to people without having to worry that they're going to be able to deconstruct your machine and figure out how it was built. For viewing the RTT file, we can actually use our RT Viewer. So you have this RT file, which is basically a lookup table of machine performance, and we use that, again, in system-level simulations. But we can also view some of the results. So we can plot things like our DQ inductance, or in this case our LD inductance, versus current and phase angle, and look at how that changes across the operating range. We can also create speed torque curves with basic control mode settings and create efficiency maps. So again, this is just a demonstration of the efficiency map and the torque speed curve that we can create using our JMAG RT Viewer tool. And finally, I want to mention too, one of the new features in JMAG version 13, which just came out in December, is that we can actually add a 3D correction coefficient to our RT models generated from a 2D analysis. So as you can imagine, if we're creating a lookup table, we have to run a lot of analyses. And typically what we do is run them in a 2D model to save time. But sometimes there's 3D effects that need to be considered to get a more accurate model. And what we can do now is add those correction coefficients and correct the file, so you can still run the majority of the calculations based on a 2D model, so they're faster, but then you can apply a 3D correction to make them more accurate. So in summary, the model-based design requires an accurate machine model, and traditional machine approximations are just not suitable to generate high-fidelity system-level models. JMAG RT can generate a high-fidelity machine block for system designers, and then that RT block can be used to simulate a high-fidelity machine in MapleSim simulation. So at this point, I'll turn it back over to John, you guys, and then can give a little bit more elaboration on how JMAG RT block is incorporated into MapleSim.
Great, thank you very much, David. So I will continue the presentation by doing an in-product demo. Okay, presented in front of you is our MapleSim product, where we have multi-domain capabilities in here. I'm beginning by showing a 1D rotational example. We also have the ability to include multiple other domains, such as on the left-hand side here, we have electrical components, the 1D rotational, 1D translational as well, our multi-body library, which allows for 3D dynamics, in which we have rigid and flexible beams and inertia components, as well as the hydraulics, thermal, magnetic library. Our focus today is mainly on JMAG. And as you can see here, we have 5 different components available to the user in the JMAG library. When someone is trying to develop a system-level model, one technique that they can begin with is to start with the bare core model. And that's exactly what we see here. It's a simple constant torque driver, an inertia, and a damper connected to a reference frame. With MapleSim, we have the power and capability provided from Maple at the core, and we can do advanced features such as what we see in my template that I have here as it loads up. This template is built into our MapleSim product, where we can see our plant model, connect directly to it, and what we can do is do an equation extraction, as the title suggests. The power of this template is to provide the user with a quick and easy way of having a symbolic representation of the actual plant model. Here we can see the equations associated with this plant, as the rotation is proportional to the drag, the inertia, how fast the device is moving, plus the torque over the inertia of that device. The relationship from the rotational speed and the fact that it's differentiated with the angle. This is all represented in a symbolic form, which is an advanced feature that Maple provides. Additionally, we can turn off symbolics and always look at the equation as a bare minimum. Here we can see that since the parameters I have currently in the model are just 1, that the equation simplified nicely. When I'm ready to move on to a more complex model, and I want to replace the actual torque driver with something that encompasses some of the other domains, such as the ones mentioned before, like the electrical domain, I can easily do that. As you see here, I'm about to enable another model available to me. Here, I've included the electrical motor with a 3-phase sine wave generator. When I run this model, the results will indicate that the overall performance is somewhat different, and we're capturing a different level of dynamics. These top 2 graphs relate to the top model, and these bottom 2 graphs relate to the lower model. In both cases, the angle increases practically linearly, and the speed converged to approximately 1 radian per second. However, you can see at the very beginning that there's different types of dynamics that are happening. When the user is ready to encompass some of the high-fidelity model capabilities that are provided by the JMAG component library, we can simply go back to our model, remove the component, and drag and drop our new component in. In this case, I've brought in the permanent magnet synchronous motor from our JMAG library. I can connect it in, and I'm ready to go. I'll be discussing some of the other capabilities that come with some of the other models later. So let's take a look in more detail as to where we'd go with some of this direction. Here is an example where we have a 5 degree of freedom robot. In our 3D viewer capability, we can see that there's CAD geometry attached to this robot. And when I run the simulation, you can see the motion of the robot behaving quite normally. Factors such as the momentum of the end effector when it moves can trickle down into the motion of the arm, as the dynamics of the system can be visually seen and do affect the overall results. When dealing with robotic modeling, a major component that drives how the overall robot dynamics occur is to control where the end effector is. And knowing how the motor accuracy, knowing the motor accuracy and how to properly control that is a major factor. This model was the development stage where we've done a basic servo motor. We've included the multi-body robot arm with the different joints, as you see here. And inside each of these arms, we can include information such as the mass and inertia properties, and translational offsets for the different link components, as well as CAD information. Our servo motors are then commanded by position drivers and are controlled with an internal closed-loop PID system. Inside this PID loop, we have our electrical motor. In this case, I've started with a permanent magnet DC machine to get the overall dynamics that I want. But when I'm ready to go and move on to higher order factors, I want to include my JMAG motor. And let's move on to what that looks like. Once again, you can see that I've reused the multi-body library. I now have a block here which represents my JMAG motor and my control strategy, and I've grouped together my command signals. In this case, I'm using a speed driver that will drive the overall system. I'm going to load the results so that we can see them as I continue discussing. Here we see our JMAG motor. In this case, it's a permanent magnet synchronous machine. I have it directly connected to the electrical system, and I can see here that my overall robot looks just as before. I have attached a PWM driver and several other components. These other components, as I'm highlighting here, represent my LD or ID and IQ phaser control system that I'm using as my speed driver. Together, that block consists of my JMAG motor control unit here. As you can see, I have 5 of them. Let's take a look at the general behavior of the robot. Once again, you can see very smooth motion, and by using my control algorithm and having account for how the overall robot behaves, I can get very smooth results. However, when we take a look at the final graph information, I can zoom in and see very subtle real-life dynamics, where we can see that the performance isn't exactly ideal, as would be in real life. We can see these subtle waveforms around our desired trajectory. In this case, this is the base motor rotating and with a slight noise as the machine moves. Since MapleSim is an acausal environment, we can go either as a motor, like we see here, where we're driving our system, or we can also operate the same components in a different direction, such as in a generator. That's the type of structure that I have in this model. once again, I'm using a JMAG permanent magnet synchronous machine. Only this time, I'm using a rotational driver to drive it at a fixed speed. This speed then drives the motor shaft, and I have the overall system connected just as I had before, only now I'm using a fixed reference ID and IQ phasor to be able to generate a specific amount of response. Once again, I'm using a permanent PWM driver to go and actually actuate the excitation field to get the overall response that I'm looking for. And what we'll see in the results, as shown here, is that the motor doesn't behave as you would expect from a textbook. In fact, it's a little bit more real to life. So on the top, these three curves represent the current response of our motor, and you can see how they generally behave in an approximate sine wave fashion, but not exactly. Let me zoom in on one of our waveforms here. You can see sharp, jaggedy lines, which are the results of the PWM driver, but you can also see a distinct sort of notch shape in all of our current waveforms, and that's the result of the high-fidelity JMAG motor. Additionally, we can also see in our torque response, as seen here in red, that this isn't a perfectly straight line. In fact, there are significant waveforms that are present in the model. This is expected with a real-life motor, as the motor wouldn't spin ideally, and now we're already capturing some of these higher-order dynamics. The green line here shows that the motor was spinning, in fact, at a constant speed based on our speed driver. The JMAG library set that we have available to us isn't only limited to the PWM, the permanent magnet synchronous machines, which I've shown so far. As seen here, I also have a stepper motor model. The stepper motor model is capable of also showing higher fidelity capabilities, where we can see that the overall response includes higher dynamics and shows that the model isn't behaving like an ideal stepper motor. The model here is a closed loop system where the position is tracked, by the input signal, and the closed loop is measured, and then the motor is commanded to go to that trajectory. I will zoom in here on my results from it to explain how they work. The green line is the motor response itself. The red line is the desired position, and the yellow and blue are the acceptable final locations, as the stepper motor has fixed steps that it can resolve to. As you can see, that the motor doesn't behave perfectly smoothly on its trajectory to the desired position, and in fact oscillates near the final value until it settles. Then once again we see the behavior continue onward when the motor is commanded to a new position. Other motor models available with the JMAG connector include the stepper motor, as seen here, the permanent magnet synchronous machine, as we've already seen, the switch reluctance motor. A linear version of our motor models are also available, such as the linear synchronous machine and a solenoid. One of the nice features about Maple and MapleSim is that a lot of our resources can be reused in different models, such as what I can see in my next model here, where I am able to reuse the development of those JMAG motors where I had in the robotic system. I can now use a new command signal response using my subsystem as I had before, where I have my control system, my PWM driver, and very much so in the most important component of this model, the JMAG motor, is located right at the heart of it. This model shows a longitudinal go-kart model where I'm now connecting it to an electric motor. I have a component right out of our standard driveline library where I'm able to include factors such as the vehicle properties. For instance, the angle of the road that the vehicle is driving on, the wheelbase, the height from center of gravity, the mass, air drag, and air density properties are available to me. I also have linear tire models attached in this case, and a simple gear ratio. We can see from the overall model that the structure looks very similar, and my approach is very similar to actually develop this, where I simply drag and drop components into my MapleSim model, and I can easily and quickly create high-fidelity models. Here are my results from the simulation, where I can see the green line here is right atop the red line, showing that the motor speed directly on the shaft is following very tightly to my desired command signal with very small ripples. Also, on the right, I can see my current response to this motor, and seeing as it's a JMAG component, we wouldn't expect a perfect sinusoidal wave, and sure enough, we can see it's fairly jaggedy and sharp. Our overall vehicle response shows that the vehicle is able to accelerate from 0 to nearly 20 kilometers an hour in the short 1.5 seconds of simulation time. On the bottom here, you can see I have a visualization to allow for a bit more intuitive approach, and we can see this in demonstration as the vehicle accelerates from a resting position on an inclination and accelerates up the hill. This concludes my in-demo presentation, as I hope to have showed you that the simplicity and use of MapleSim and how effectively they connect in with the JMAG connector. We'll turn it back over to Orang to conclude our presentation.
Thank you, Jonathan, and thank you, David. So the key takeaways, we talk about physical modeling, which is important for doing a complex system and helps towards the engineering system design, testing, and integration. The symbolic technology which powers Maple and MapleSim, and their role in creating models in a causal fashion and also creating fast code. We've seen the JSOL PowerShift solution and Maplesoft, which they come together to provide this high-fidelity model of mechanical system in the system-level modeling environment of MapleSim, which is now available and will provide rapid integration for detailed models. And we have also, I've also touched on the Maplesoft engineering solution, which together with the tools that we have, that expertise could help our customers to create better solutions faster and be more successful.